Section 12.3, conic sections, hyperbola. We're in our third of our actual four conics, circles being the first one, but again, that was the previous chapter. So hyperbola, definition is the set of all points P in a plane such that the absolute value of the difference of the distances of P to two fixed points in the plane is a positive constant. So this is similar to our ellipse where we had this length D1 and D2, which is always a constant. We're going to have the same situation here for this hyperbola. We'll see a diagram here in just a second. Some more similar terms, focus again showing up. And we have two of them just like with the ellipse. And like the parabola, the focus will be wrapped up by what we call the branches of the ellipse. They'll be kind of like the same thing a parabola does, wraps around the focus. So does the hyperbola here. The vertex, this is the point on each branch that is on either end of what we call the transverse axis. The transverse axis is the line segment that connects two vertices. And we have a conjugate axis, which would be the one that's perpendicular to the transverse. So don't think of these like major axis and minor axis of an ellipse. They're different. Then the center is actually a point that we don't go through, kind of like the ellipse. We don't draw our ellipse through the center of it. And the center of a hyperbola is, again, a point that we don't go through physically with the graph, but we use it when we translate the graph, or we use it to help ourselves determine these conjugate and transverse path lengths. So here we have the diagrams of the two different scenarios. One where our parabola has branches, and the branches are these guys right here. And we have branches that are opening left and right, which means our transverse axis is the blue one, would be on the x-axis. And then we have the conjugate axis, the red one, going to be perpendicular to it. And notice it's the transverse axis that kind of houses all of the critical points in terms of our drawing. It's where we're going to find our focus. It's where we're going to find our vertex for each of the branches. The conjugate axis point that we see here and here, in conjunction with the transverse axis points, actually helps us determine these corners of what we call our asymptote rectangle. That asymptote rectangle helps us to determine one way to determine what our asymptotes are. Those are those dashed lines. We actually have an equation we can use to find the asymptote as well. So transverse axis on the x, and then here in the next example, transverse axis on the y. So now my hyperbola is opening up and down. Conjugate axis perpendicular to it. Okay. Here are our standard equations with, again, centers at 0, 0. And you're going to see over in the diagram we've got some other shapes that we're using to help draw our hyperbola. Our hyperbola is actually just the purple curves that we see there, but we do have some help from some other shapes. One of those shapes being what I just talked about, and that's this rectangle that we call our asymptote rectangle. How I find the values for that are determined on what my transverse axis half length is and what my conjugate axis half length is. So once I find A's and B's, I'm able to determine what this box shape looks like. We'll use the same variable for the foci, so C's again. And here, because this has a transverse axis on the x, that means our hyperbola is opening left and right. Our vertices will be our x-intercepts, positive, minus, plus, minus the a values. And this graph has no y-intercepts. It's not intersecting the y-axis at all. So don't misinterpret your conjugate axis values of b and negative b to be actual intercepts. They're not points on the curve. I mentioned in the previous section with the ellipse that we have this equation that has c squareds and a squareds and b squareds that helps us find either, given a foci value, find the other a or b's. And in the ellipse equation, it was c squared equals a squared minus. Now, notice the difference here from our ellipse equation to our hyperbola. And then, again, we're pointing out the fact that this equation, c squared equals a squared plus b squared, is a plus, where in the equation for the hyperbola itself, there is a negative. And it was reversed of that from our ellipse equations. So our hyperbolas look a lot like our ellipse, except the fact that we have a negative in between. And in our ellipse equations, I talked about some locked values. I talked about how x squared and y squared stay where they are. And that is different in the hyperbola. In the hyperbola world, the a squared and the b squared are locked in position. They stay there. And our x's and our y's will switch. So here are those vertex points that help me define that point of each branch. And again, that's what this thing is called, branch. Vertex is located on the either end of our transverse axis. Same equations as we had for our ellipse, 2a and 2b, but it's not major and minor, it's now transverse and conjugate. And here are the equations, plus or minus b over a to the, or b over a times x equals y. Those are the equations we can use to find out our asymptotes. And again, these lines right here are our asymptotes. Once again, line that we will approach, but we won't cross this. These are oblique asymptotes. So there it is, transverse axis on the x. Let's switch it up, put the transverse axis now on the y, and we have our vertices now on the y-axis. Notice, though, that y squared and x squared have swapped versus the previous example. The a squared and the b squared locks in position. Y's and x's are now flipping. Okay. And this tells us that our transverse axis value, which will always be the a, is related in this case to the y, meaning it's on the y-axis. And then here, our transverse axis value, a, related to the x, meaning it was on the x-axis. So those two transverse a's and the value of the variable above it, either y squared or x squared, will help you determine what kind of an axis we're referring to. So now we have our y-intercepts, you'll notice, that have a plus minus a value. Those are our vertices. And again, our foci has changed, so now we're on the y-axis for our c values. One other thing that changed is our equation for our asymptotes. Y equals plus or minus a over b times x. Sketch the graph of each function. Find the coordinates of the foci. Find the links of the transverse and the conjugate axes. Okay, this is going to be very similar to what we did with our ellipse. This equation right now does not look anything like the standard ellipse equation that we've had until we decide we want to make this thing equal to 1. So we divide by 144. We get x squared over 36 minus y squared over 4 is equal to 1. Again, it's that negative sign that's telling me that this thing is a hyperbola, not an ellipse. All right, we said the a and the b is locked in place, which means this is equivalent to my a squared, and this is equivalent to my b squared. And the a is related to the x, which means my transverse axis will be on the x. So let's just go find all of the parts here. We got a squared equaling 36. That means a is equal to 6. B squared equals 4. That means b is equal to 2. Now there's a plus or minus again. How about c squared? You know, it's a squared plus b squared. 36 26 plus 4. So c squared equals 40, which means c is equal to the square root of 40, which means it's 2 root 10, plus and minus again. So from that, we know our foci are on the x-axis at 2 root 10, 0, and at negative 2 root 10, comma 0. Those are our two foci points. All right, let's generate this rectangular asymptote rectangle so that we can help ourselves draw the asymptotes. Again, I could use this plus or minus b over ax. I know my b is 2, I know my a is 6, so we're talking about a 1/3 x plus or minus for my asymptotes. I wanted to draw them that way. Well, let's take a look at the rectangle, see if that might be helpful to you. All right, transverse axis. If our a is equal to 6, that would mean that the length of our transverse axis, well, first of all, 6 being we're coming from the center, right? We're going to be having our center at 0, 0, 0 here. So if our a is equal to 6 plus or minus, that means I'm going to go right 6, and I'm going to go left 6. And we get a point there and a point there. Now those 2 points are actually my vertices. So I know that I have a vertex at negative 6 and positive 6. And again, that's because my transverse axis is where my vertices lie. And so a equaling plus or minus 6 tells me that I have 9 points there. My b is a 2, above and below. And so with the help of the 6 and 2's, I'm able to think about my rectangle that's generated here. So right 6 up 2, right 6 down 2, left 6 down 2, left 6 up 2. And this then is that asymptote rectangle that I was referring to that we could use to help me draw my asymptotes in. And the asymptotes are going to go through the corners. So I know one of them will look something like this. All right. The other one will go through the other corner. And look something like that. So those are my asymptotes. I don't need to be such a thick line, but let's see. How's that? All right. We know where our vertices are. There they are. That point and that point. So I can sketch what my hyperbola is going to look like. I'm going to be stuck in between these asymptote lines, and so I'm going to get something that looks like this. I'm going to be coming from in here, and then doing that kind of a thing, and doing the same thing on this side. Something like that would be what this hyperbola is going to look like. In terms of the foci, where are they? They're going to be, again, they're going to be hugged. If we think of it that way, we're going to be surrounded by these branches. So we have a negative 2 root 10, and negative 2 root 10 value is a negative 6.32. So we're just past that 6 mark, so one of my foci we'll call F prime is right there, and the other one is going to be right there. This one will be F, this one will be F prime. All right, did we get everything? We have our lengths of our transverse and conjugate axis. Nope, we didn't do those yet. All right, so our transverse axis is 2 times A, which is 2 times 6, which is 12. Our conjugate axis is 2 times B, which is 2 times 2, which is 4. So there's our major, or our transverse axis length. There's our conjugate axis length. And we can actually see it. Here we go, -6 all the way to +6 is 12 units. -2 all the way to +2 is 4 units. So there are your 2 axes. All right, I believe that we have hit everything graphic-wise. Let's take a look at this one. And again, numbers. Notice that the numbers of these, the coefficients and the constant, coefficients have just been swapped. And look at the positions of x and y. The top one we have x squared, then y squared. And this bottom one we have y squared and x squared. So we're going to talk about these guys. These are known as what are referred to as conjugate hyperbolas. Y squared over 4 minus x squared over 36 is equal to 1. All right. Remember we said A and B is locked in place. So this is your A squared. This is your B squared. So we can go ahead and find A is equal to 2. And then why don't we go ahead and just find the length of our axis here. So 2A is going to be equal to 4. And that is going to be our actually our minor. This is our conjugate axis length. And how we know that is it's it's our transverse axis length. And we know that because, again, it is with our A value telling me that my transverse axis is going to be my y-axis this time. So my vertices are going to show up on my y-axis instead of my x-axis. And b squared, which is a 36, tells me b is equal to 6, and 2b is equal to 12. This is my conjugate axis. So we don't want to think that the bigger number is always your transverse. That's definitely the case here. Smaller numbers are transverse axis, and it's because our y squared is with the A. Remember, whatever is with the A is your transverse axis. Okay, why don't we go ahead, while we're still crunching through some values here, let's go ahead and find C. So we have A squared plus B squared. A squared is 4. B squared is 36. So once again, we have C equals the square root of 40, which again is a 2 root 10. Which means my foci, now that we're having a vertical transverse axis, my foci is 0, 2 root 10, and 0, negative 2 root 10. There's where they lie. And let's go ahead and sketch this thing. So transverse axis, value of 2 above, 2 below. There we go. There's my transverse axis of length 4. My conjugate axis, B's are 6. I'm going to go out here and here. And you'll notice it's the same asymptote rectangle that we have in the other one. Which means I'm going to get the same. Just copy these guys. I have the same asymptote ones. There's that one. two asymptotes. Again, our vertices are on our transverse axis, so they're here, which means my graphs are going to open, my branches are going to open left and right. I mean up and down, because my transverse axis is vertical. Foci, where are they? They are, what did we say that value was? I think it was 6.32. So I'm going to go 6.32 up, 6.32 down, and this would be my F, and there's my F front. All right, so that's where our foci are located, and this is what this thing is going to look like. Oh. This is what this thing is going to look like. If it cooperates. No, it's not cooperating. With that equation, I'm going to have to fool it and use these guys. All right. So this is going to actually do it in pieces. Top piece. Whoops. And bottom piece. There we go. So there we go with our hyperbola for this example. Purple and red. And once again, those two, they shared the same asymptote rectangle. They had different positionings in terms of the y's and the x's, but you'll notice that the 36 was the coefficient with y all the time for both equations, and the 4 was the coefficient with the x's. Those are called conjugate hyperbolas, and they take on this form. So this m and n thing, it's just intended to point out that the m's stay with their respective variable, in this case, the x's, and the n's are hanging out with the y's. So we will see those as a squareds and b squareds again, but this is just trying to show the relationship there for conjugate hyperbolas. They share the same asymptotes. All right, finding the equation of a hyperbola given the following and in the form of. I'm going to peek ahead here just a second. All right. We have a length of a transverse axis is equal to 10. Now, again, transverse axis, we know, is referring to an A value. So I have 2A here is equal to 10, which means I've got A equal to 5. The conjugate is referring to the B values. And we get a B of 10. All right. We are in this form, x squared minus y squareds. And we've already established the fact that what's down here is locked in place as an a squared, and what's here is going to be a b squared. So we have that form, which means my transverse axis is going to be on the x-axis for this one. We now have a, we now have b. We can write the equation, x squared over 5 squared minus y squared over 10 squared equals 1. And so we get x squared over 25 minus y squared over 100 is equal to 1. And there's that equation for that particular given set of information. Here we have length of transverse axis is an 8. So once again, we know the relationship between transverse and variables means we're talking about our A value. Notice our form is different though. Now we have y squared over our A. This tells me that my transverse axis is now the y-axis. Distance of the from the center to the foci. So here we have a situation where I don't know what my b is. This is very similar to the ellipse problems that we had done. I do know distance of foci is this c distance. And because we're on the vertical axis, my foci are going to be 0, 5, and 0, negative 5. But we need to know b. Well, that's why we have this equation. So our b squared is equal to c squared minus a squared. So we have 25 minus 16, giving me a b squared equaling 9. So a b is equal to, again, a plus or a minus 3 value. That tells me left and right 3 would define, help me figure out what my asymptote rectangle looks like if I were to draw the sketch of this thing. But we weren't doing that. We were just writing the equation. So now that I know what a and b are, we can go ahead and fill in a squared, which we know was 16, and our b squared, which we know was 9, and that would have been the equation for this example. So a lot of stuff to kind of keep track of, and it's very easy to get it all confused. All right. System of equations, we are going to revisit systems, and remember what a system is. A system is two or more equations, and graphing-wise, we think of them being graphed on the same coordinate system, and we look to see where there are intersections between the two, and when we find an intersection, we know we have a solution. So an intersection denotes a solution to our system. All right, so we're going to graph both of these guys on the same grid here and see what happens. All right, we look at the first equation. We see a y squared minus an x squared. That should clue us in right off the bat that this thing is a hyperbola. Maybe not so obvious as what this one is. We see y squared and x squared, you might think, oh, that means I have an ellipse. But notice the arrangement of x squared and y squared. In an ellipse, x squared and y squared are locked in position. And also, there are no coefficients in front of y's and x's here. So what makes the second equation a little weird is that if I tried to make it an ellipse and divide everything by 5, I'm going to get a 1/5 and a 1/5 equal to 1. I have the same major and minor axis lengths. And that would mean I've got a circle. So this is actually a circle. And the equation of a circle is x squared plus y squared is equal to an r squared, or a radius squared. So what that tells me is 5 is equal to my radius squared. That then means my radius must be plus or minus. Although we're talking about a length, so I don't need to have plus or minus. My radius is equal to the square root of 5. All right, so we know we're centered. Both of these graphs are hanging out, but their centers at 0, 0. So I'm going to real quickly put the sketch up so we can get down to business here. There we go. There's our circle. The next graph being a hyperbola. After I edit this thing, divide by 3, I'd have y squared over 3 minus x squared over 3 is equal to 1. Same conjugate and transverse axis lengths, but how do I know which axis we are on? Again, here's the relationship. This is my a value, and that means I'm on the y-axis for my transverse. So I would go and I'd find all of my respective parts. So a squared equals 3 means that a is equal to the square root of 3, and that's the same thing as b. And we would plot those. We would create our rectangular asymptote rectangle help us draw this thing, and it should. Oh. No, not graphing that one right again. So we're going to have to do this one ourselves. Let's see, square root of 3, 1.7. All right, so 1.7, and we're going to go transverse, which is our y-axis. 1.7 up, 1.7 down. That would be our vertex. I would be the same distance away from my B, or my conjugate axis, 1.7 right, 1.7 left. I would then be able to generate my asymptote rectangle. So it's going to look something like this. My asymptotes. And my curve would do something like so. Hyperbola bottom, hyperbola top. And you can see that we have all right, and we can see graphically that I've got some intersections going on here. I bet if I drew my graph a little better, it would probably be around those, what, 1, 2, 1.1 something. All right, anyway, we're not going to guess. We are actually going to use algebra to figure out what those intersection points are going to be. So this is now going back to our system days, except now we're not dealing with linear systems, we're dealing with conic systems. And we solve systems by either elimination method or substitution. So I'm going to have my two equations, y squared minus x squared equals 3. And y squared plus x squared equals 5. And the way this is set up, it's actually conveniently set up for me to do elimination. My x squareds are already set up to cancel each other. So I get 2y squared is equal to 8. Then divide by 2, y squared is equal to 4, y is equal to plus or minus 2. All right, and it looks to be about that. That's about right, where we're intersecting on that circle and the hyperbola there. But those are only the y values. And now we got to go find the x values. So don't forget, you're looking for coordinates. So don't just get all excited to stop here. We got to go find x's. So we're going to choose to plug into one of my equations. And I'm just going to go ahead and plug into this one. We're going to solve for x. So we're going to put a 2 in there. We're going to square it. Minus x squared equals 3. And we end up with x squared is equal to 1, which means x is equal to plus or minus 1. And that would be the same thing had I plugged negative 2 in there, because negative 2 squared just gives me 4 again. So with these two, I am able to see I have actually 4 different coordinates. One of them, and here we'll show the math for the other scenario. I don't need to show positive, negative 2. I'm going to get plus or minus. So I'm going to have 4 coordinates. I'm going to have a negative 1, positive 2 intersection. I'm going to have a negative 1, negative 2 intersection. I will have a positive 1, positive 2 intersection. And a positive 1, negative 2 intersection. And you can actually see all of those up in the graph. So these are my solutions to this system. Those are the only common x and y values that those two equations have with one another. So this is good little practice for graphing. It's also a good review of our algebra for solving a system.